Well, good morning, everybody. Thanks for coming back to another sprinkler talk on Thursdays at 10 a.m. Today's presentation is going to be on sprinklers and mist systems. So remember last week we talked about residential systems. That was part one. This is part one, sprinklers versus mist systems. As I said before, not quite sure how many parts there'll be. I'll just keep going until I've kind of gone through all the information that I've got. But yeah, there'll be at least one more part for mist systems, but I imagine there'll be 3 parts. But we will see how the time goes and see how much we can fit into to these sessions. As before, these sessions are. I mean, I aim for 20 minutes originally, but I think most of them have been more towards the half an hour mark. But I think anything under 30 minutes is still fine, really. But yeah, I don't want to kind of overload you with information with each session. So yeah, we'll start proper in a couple of minutes' time. Let's say at 10 o'clock. But so yeah, I'll speak to you all again very shortly. Okay, right. It's 10 o'clock. So yeah, let's go. Let's be prompt. So yeah, sprinklers versus mist systems then is the topic of today's presentation. I'm going to start a little bit like I did with the biofilming and Legionella presentation with a little disclaimer and just say, that first of all, I'm a sprinkler guy. I've been working at Project Fire for 8 years now, I think. So I know sprinklers reasonably well. I'm less of an expert on mist systems, so yep, just have to bear with me if I say something wrong or whatever. I do my best, obviously, to make sure that all the information is accurate. But yeah, I know less about mist systems than I do sprinkler systems. What else was I going to say? Yeah, and I'm also slightly biased towards sprinkler systems as well. So I would kind of admit to that from the outset. Is again, because of my background in sprinkler systems, if you in certain kind of business world, you need to declare sort of a conflict of interest. Well, yeah, I've got a conflict of interest because I work for a manufacturer of products for the sprinkler industry. So just kind of get that out of the way to start with. But so I do hope that the information that I give you is correct, and I do hope that it's useful as well. And obviously, it's a platform for discussion, really, rather than me sort of telling you, exactly how everything works and what the advantages and disadvantages are. It's something to kind of start a conversation with. Okay, well let's get into it then. So, first of all, let's define what we mean by a mist system or water mist as opposed to a sprinkler system. Really, this is down to the size of water droplets which are created. That's the key difference between these two types of system. There will be some kind of grey area in the middle, but this is the main thing that we're talking about, is how big the droplets are. Mist systems create smaller water droplets. Here is a quote from British Standard 8458, which is one of the British Standard for Watermist systems. And this gives a definition of what we actually mean by water mist, which is shown on the screen here. Water mist is defined by water spray with the size dV 0.9 is less than 1,000 or 1 millimeter. So this is dV 0.9 is talking about the deviation 0.9. So what that means is that 90% of the droplets that are created. Mu-m or um, that is a micrometers. So 1,000 micrometers is 1 millimeter. So they're saying that 90% of the droplets will be smaller than 1 millimeter when generated under the minimum operating pressure and distributed onto the surface of 1 meter from the nozzles. So I've not actually seen this kind of done in real life, but I'm imagining that they have some sort of screen. They set off the nozzle at 1 meter distance. They run it at the minimum operating pressure, and then somehow they use some sort of camera to then analyse the size of the droplets which are created, and say if 90% of them are less than 1 millimeter, then it would officially be water mist. Again, this table down here, I've taken this from various sources around. So again, I think it's accurate, but I'm not entirely sure. Sprinkler droplets are generally larger than 1 millimeter. How big, I'm not quite sure. Mist droplets say, although 1 millimeter or 1,000 micrometers is the kind of the cut-off point, a lot of mist systems are dealing quite a bit smaller than that, at the region of 150 to 300 micrometers. But as I will say, quite a lot during this presentation and future presentations about mist, it will depend and vary from manufacturer to manufacturer. If the droplets get even smaller, then we get into the category of fog. So fog, again, even smaller droplets. And I'm suggesting there 50 to 150 micrometers for fog. And then if the droplets get even smaller still, then we could refer to them as aerosol, which is, again, I'll put here less than 50 micrometers. So all this is based on the size of droplets which are created. Now, there are systems out there which describe themselves as fog. So some of them are kind of officially fog because of the size of the droplets. Some of them, they're called fog, but really, I think technically they would still be a mist system. But like I say, that's all of this information is quite loose, really. There's very few sort of defined sort of cut-off point when one droplet becomes one and something else. But you get the idea. It's all to do with the size of droplets. Sprinklers have a larger droplet size than mist systems, is a very, very key difference between the two systems. This is a sort of a visual sort of look at how the droplets are created and how the different size of the droplets is kind of shown in a kind of visual way. Now, I have put on here unscientific, so I do totally appreciate that. It obviously will depend on the type of camera that's used and the kind of the shutter speed that's used. So, it's not a perfect illustration, but I think that this kind of helps to show what I'm talking about here. Is that on a sprinkler system, it's kind of like being under a shower head. That's a sort of experience you're going to get. You can actually see the separate droplets sort of coming out. On a mist system, it is more like a spray. The droplets are much smaller, and you can actually see that visually when they are set off. A little bit of background for you now. So Watermist has been around a very long time, almost as long as sprinkler systems, really. Back in the day, I suppose, there wasn't such a distinction between a sprinkler system and a mist system. Because mist systems generally require higher pressure to create the smaller droplets, they did come a little bit later when technology was a bit better to create that higher pressure that's required to create them. But yeah, people were kind of playing about with mist systems, quite a long time ago, which for me, stands to reason. Any kind of sort of inventor, science person is going to think, okay, well, what happens if I make the droplet smaller? What effect is that going to have? What happens if I increase the pressure? They're going to play about with the distances between the heads, the activation temperatures, the different spray patterns. All of this kind of experimentation has been going on, which obviously boils down to a very reliable product at the end of the day. But mist systems never kind of had the same sort of standardization in the early days as sprinkler systems did. Sprinkler systems very quickly were established as a kind of very standard practice with rules and codes to follow. Mist systems didn't have that quite so much, say, back in the early days. A couple of things to pick up on, though. So this is the Scandinavian Star Fire in 1990. This was a passenger ferry, so it has passengers and cars. 159 people sadly passed away in this tragic event here. Again, one of these events where lots of theories in terms of what happened, lots of books been written about it, whether it was an arson fire or something else. So it's still kind of up for debate. But what this did do is it really made the kind of maritime organisations as a whole really look at safety, fire safety aboard all sorts of vessels, but particularly passenger ferries where you've got a lot of people sort of crammed into a small space. How can we make them safer? And Watermist was one of the things that was really pushed forward. So Watermist was and is very common on board this kind of vessel. It might be just in the kind of machinery spaces and the kind of engineering spaces. It might be just throughout the decks, in all of the kind of the life safety environments as well. That was a big thing that kind of pushed mist systems very much into the forefront for kind of maritime organisations. Another key thing for Watermist was the ban on the use of halons. So halons, in particular halon 1301, is an excellent product for fire suppression. It's got a lot of advantages to it, and say, back in the kind of 70s and 80s, this was the thing that was being used quite widely, again, mostly for specialist risks, but it was a really good material to use. A little bit later, we'll talk about the fire triangle. Halons kind of don't tackle any of the kind of traditional sides of the fire triangle. But what they do is they kind of chemically interrupt the combustion chain. I don't 100% understand that, but they kind of stop the molecules sort of bumping into each other. They stop the combustion process happening. That's kind of how they work it in very brief. They're non-toxic in the levels required to fight fire. So they're kind of safe for human contact. There's no cleanup. They're very efficient, very effective. So, excellent material to use. But it is a CFC. And as you know, that was identified as a major source of global warming and damage to the environment. So in the Montreal Protocol of 1987, it was agreed to ban the halons, and this was extended at the Kyoto Agreement in 1997. So that was kind of gone. The reason why I've got Eurotunnel on the screen there is because Eurotunnel was one of the last kind of major projects to use halons as the fire suppression system. So yeah, Watermist kind of came along and plugged the gap really, where in the past they would have used halons. Watermist was sort of pushed forward as a solution for these kind of specialist risks, where you can't use halons anymore. Then Watermist was an option to put in its place. So yeah, let's look at the fire triangle though. So this is kind of going back to basics. So if you want to put a fire out, you need to tackle at least one of these kind of elements to put the fire out. So fire, as we know, needs oxygen, it needs heat, it needs fuel, and when those things kind of come together with an ignition source, then we get a fire, which is this kind of chain reaction of combustion going on. So some options: we can remove the fuel source. So if we take away, there's nothing to burn, then it can't burn. If we take away the oxygen, so we kind of smother it. That's kind of what the fire blankets do. We can put that over the top. We can cut off the oxygen supply. That will put the fire out, albeit temporarily, of course. You know, if we lift the fire blanket back up again, oxygen goes back in. The whole thing could start again. And heat as well. If we cool the materials to below their flash point, then they will stop giving off the gas, and that's that kind of gas that is actually burnt within the fire. But that's why, you know, if you look into a campfire, it's not really the wood that's on fire. It's actually the gases that are given off by the wood which is on fire. If you kind of look closely, you'll kind of see what I mean. So yeah, if we can cool the fire down, again, we can put the fire out that way. And say that the halons kind of interrupt the chemical reaction which is going in, which is another one. So sprinklers and mist systems are both tackling the fire, and they're kind of doing a combination of these things. So by adding water to the fire, which is obviously what we're doing in both sprinklers and mist systems, we're putting water onto the fire. That water has a cooling effect. That water is I don't know, it's kind of room temperature, isn't it, I suppose, when it goes onto the fire. So it's, I don't know, 20 degrees, 15 degrees, something like that. The kind of temperature you expect to find out if you cold water tap. So that's going to cool the fire down. There's also another element to it we'll come on to later. Removing the fuel source. Well, sprinklers don't really remove the fuel. What they do is they get the fuel wet. And obviously, a wet materials generally are going to be harder to burn because they're wet, and we need to kind of get evaporate the water out of them first. So in a sort of classic Class A fire, where we're talking woods, paper, plastics, that sort of thing, by getting the material wet and also the surrounding material wet, we are, in effect tackling the kind of fuel element of the fire. And both sprinklers and mist systems have an effect of smothering as well, because we're kind of introducing these water droplets. The water droplets actually kind of boil, if you like. They turn from water droplets into water vapor, into steam or water vapor, and by doing that, they do create a kind of a smothering effect at the top of the fire as well, to stop more oxygen getting into it. So both sprinklers and mist systems tackle the fire in all three of those kind of ways, but they have sort of different strengths and weaknesses. And the main sort of strength of a mist system is by cooling the fire down. So a sprinkler system will cool the fire down, but a mist system will do it more quickly and more effectively than a sprinkler system. Excuse me. Doesn't mean to say that mist systems are better overall for tackling fires, but it does say that the mist systems very much concentrate its efforts on cooling the fire down. So let's look a little bit into that. So this is going back to our physics lessons. The states of water, solid, liquid and gas, so ice, water, and then water vapour. And the red line here is to do with the energy, and so we've got heat energy on the kind of x-axis, and we've got temperature on the y-axis. And what that red line is showing you is when you add heat energy, the temperature of the water increases. And as we know, when the water gets to around 0 degrees, it's going to melt. It's going to turn into liquid. Excuse me. So the red line isn't a straight line. So when the water is actually changing state from one thing to another, you're actually putting heat energy in, but you're not actually getting a temperature increase. And why is that? Because you need to add energy to break the actual bonds between the molecules in order to separate them out. And that's essentially what you're doing. The solid, all of the molecules are quite tightly joined together. In liquid, they're kind of split up into smaller patches, and in gases, they're very much split up as well. So that's why that red line isn't straight. And we can actually use that to our advantage when it comes to cooling the fire down. So let's imagine we want to heat up some water. We want to heat it up from 70 to 90 degrees. So to do that, we need to put in an amount of heat energy. You see, I've got no units on my graph, so it's just some energy, and then we get a some temperature increase. So I say, kind of a medium amount of heat energy, you get a medium amount of temperature increase. However, if we then want to increase the temperature from 90 degrees to 110 degrees, okay, so we're still going up 20 degrees, but we're now on a different part of the graph. And the point is we need to add significantly more heat energy in order to achieve that. And that's what happens when we add water, or particularly mist droplets, onto a fire. The mist droplets heat up and they go through the kind of the 100 degrees. They get turned into water vapour, and to do that requires a significant amount of heat energy. So we're basically sucking heat energy out of the fire in order to turn our water into water vapour. And so it's that effect which has this kind of major cooling effect on the fire. And the mist system does it better, does it quicker, does it more effectively than a sprinkler system because the droplets are smaller. And that's down to surface area, which again, I'm sure you're kind of familiar with this concept. Here's a cube here, so we've got a side length of 10, so the area is 10 by 10, 100. The surface area, well, we've got 6 sides, so it's 100 times 6, 600 units is our total surface area. Our surface volume, again, so the actual volume of the cube is 100, sorry, is 1,000, 10 by 10 by 10. If you split that cube up into 6 pieces, so you see that the total volume is exactly the same. Okay, we've not added anything, we've just cut it up into smaller pieces. We've now got a total surface area of 1,200 or 1,200 units. If we split that cube up again, so each cube has been split into how many parts was it? 6 or 8 parts. Then again, the total volume is exactly the same, but the surface area increases to 2,400 in this case. So that's just, again, I'm sure you know that already, but by increasing the surface area, it means that the water droplets are going to heat up more quickly, and then they're going to have this cooling effect more rapidly. Okay, moving on. Typical sprinkler head, should be familiar with this by now. So we have the glass bulb as our activation. We have that kind of copper-coloured device, which is like a plug, which is holding the water back, and we have our deflector plate, and that is what is creating the droplets. Okay, so the droplets are being created by the water hitting that deflector and then breaking up into smaller droplets. These are mist nozzles. Okay, so I don't know for why, but we call the sprinklers heads and the mist stuff nozzles. So heads and nozzles. So the mist nozzles, the main difference is that they don't have a deflector plate. So the droplets are created by the water being pushed through a small orifice. Okay, so that the droplets kind of happen naturally, if you like. If you push water at a high pressure through a small hole, that will naturally kind of spread out and create water droplets. You can see some of these nozzles have got glass bulbs. The one's shown a yellowy orange coloured, but yeah, you can get red ones as well. There is a red one on the screen, isn't there? So yeah, just like sprinkler heads, different coloured bulbs, different activation temperatures. But you can see some of the nozzles haven't got glass bulbs in them, so they are designed to activate like a deluge system. So all of the nozzles will go off at once, or in an area, say depending on how the system's set up. But the point is they're not activated individually, they're activated via some other system. So it could be a manual push button, or it could be a smoke detector, or something that's going to detect a fire in the room, and then it will activate all of the nozzles within that room. But yeah, the main point is that the droplets are in a sprinkler head are created by hitting the deflector plate. In a mist nozzle, they're created by, say, forcing the water through a small hole for small orifice. System pressures, let's talk a little bit about that. So sprinkler systems, under 12845, we talk about a maximum of 12 bar. Now, sometimes you do get a little bit higher than 12 bar if you've got a high-rise building. Some of the risers, some of the kind of equipment by the insulation control valves, they may well be higher than 12 bar. But in terms of actual the water behind the sprinkler heads goes maximum of 12 bar. Typically, a lot lower than that. I mean, again, we don't want to add pressure to the system unnecessarily. So essentially, we're going to have the lowest pressure we can have while still guaranteeing the minimum pressure at the sprinkler heads. Then we have low pressure mist, we have medium pressure mist, and we have high pressure mist. Now these figures can vary very greatly. Again, for me, I couldn't find a kind of recognised document which kind of said, okay, that's low pressure, that's high pressure. So again, this information I've collected from various sources and sort of used my own thoughts really to put this together. So low pressure mist, typically below 15 bar. So actually, you can see there is some overlap there between a low pressure mist system and a sort of a medium to high pressure sprinkler system are going to operate on a kind of similar pattern. Medium pressure mist between 15 and 50, high pressure mist anything over 50 bar, but they can be over 100 bar in terms of operating pressure. Again, you'll get used to me saying this, varies from manufacturer to manufacturer. Sprinkler systems are very sort of standardized. So if you go to different contractors and ask them for a sprinkler system, you'll get quite a similar system, really. With a mist system, if you go to different manufacturers, you'll get a completely different system and completely different components, completely different operating pressures and kind of principles behind it. Watermist claims. Okay, so we're going to go on to this next week. Okay, so not next week, next session, next Watermist part 2. I'll be looking at some of these claims that Watermist makes. Okay, so we'll just go through them quickly. Smaller water storage, cheaper, reduced water damage, suitable for a wider variety of fires, more environmentally friendly, better looking, smaller pipe diameters, tested, compliant and approved, and good for property protection. Okay, so those are the claims that Watermist are making, and you'll kind of tell by the kind of the tone of my voice that some of these I'm going to say are absolutely true. Some of them I would say are not true, and some of them are either a little bit in the middle, a little bit kind of misleading perhaps. So say in part 2 I'll be going through these claims and kind of examining them in a bit more detail and sort of looking into them. So yeah, coming up in part 2 we'll be examining the claims of Watermist, looking at some arguments against Watermist, looking at the kind of the fire categories and what applications Watermist is going to be suitable for. looking at some extracts from other articles and other relevant people. So, it won't just be my opinions. I'll be quoting from other articles and other people that have written about this subject. Looking at some example diagrams of Watermist systems, and looking at the standards that are available for Watermist. So yeah, thanks again for listening. Say there's a lot more to come on Mist systems to enjoy in part 2. Next week we're going to be looking at sprinkler system commissioning. So we're going to be looking at what you have to do when it comes to handing over the sprinkler system. So I suppose my angle on this is going to be coming from a building owner's point of view. Sprinkler people should know what they're doing in terms of commissioning anyway, so I don't need to teach them. But what I think would be useful is sort of putting yourself in the shoes of a building owner or an AHJ, an authority having jurisdiction. You're kind of attending site for commissioning of the sprinkler system. What kind of questions should you be asking? What sort of things should you be witnessing? How can you be sure that the sprinkler system that is sort of being demonstrated and handed over to you is actually fit for purpose and does what it's supposed to do? So that's kind of the angle that I'll be coming at it from, is how to ensure that you've got a fit for purpose sprinkler system at the day of handover. So I'll be going through all of that next week. So yeah, hope you can join me for that. Let's have a quick look for questions. Okay. Bit of a cheeky comment there in the chat. You can read that for yourselves. Okay, thanks a lot for joining me, and hope to see you next week. All right.